All right, so let's carry on with SVMs. Second part. So if you recall the previous session when we started to talk about SVMs, we mentioned that they are more robust to noise. So as a recap, I brought out the slide we discussed in the previous lecture. So we mentioned that these data are prone to noise. So the higher the noise is, every time you have to change your classifier, right? So instead of doing so, what if we find a way, what if we find a good margin that is robust to noise, so that the thicker the margin gets, the better it's tolerant to noises. So we would like our margin to get fatter and fatter, right? And we call this either P or rho. Could compute this. All right. So that was the idea. We reached the point that for the equivalent formulation, we mentioned that this is a quadratic programming formula. So we need to minimize this value, 1/2 of W transpose W, right? Such that Wn multiply, which was the real value of the class, +1 or -1 in a case of binary classification, right? So Wn multiply W transpose Xn plus P is always greater or equal than 1, right? For all the n's. So that was the formulation that we need to solve, right? And we mentioned that this is equivalent to the previous formula that we talked about it last session, because at minimum, you see at minimum it brings 1, right? So the solution space strictly holds for this equivalent formulation, right? So now let's have an example to see how we're gonna formulate, given some n's, right? How we're gonna formulate this optimization, and how we're gonna find the W star and B star, which are the optimal parameters of our hyperplane, right? Say that was your 1x2, right? If you find solving this, you're gonna find W star and B star, and you can, given your data, you can find this line, right? All right. So now let's have a look at the first example. So we have these 4 x's. x1, x2, x3, x4, and their corresponding labels. So x1 was labeled as -1, x2 was -1, x3 was +1, and x4 was +1, right? If we draw this, we're gonna have this diagram, right? So we need to find W star and B star here, right? So the line we want to find finally that classify this using SVM is L. So it has W1 x1 plus W2 x2 plus the bias form. So we mentioned bias first here. So we have to minimize this. This is equivalent to that previous slide. WT W, right? And this stands for subject to, or such subject to, or sometimes they call it such that. So ST. So we need to find the optimal parameters W star and B by solving this, right? Let's see how we're going to do that. If you have some time. So I'm not sure if you have taken any courses previously that that were teaching you optimizations, operation research, quadratic programming, or something. Did you have one in your undergrad? No. So this is completely new, right? Okay. I mean, that's pretty easy. Don't worry. So we need to minimize this value 1/2 W1 square W2 square given this constraint, right? And this constraint has all the x's, right? And I have 4 x's. So I can generate 4 of these constraints given each of my x's, right? So let's see how we're going to do that. We saw that x1 was here, x2 was 2 and 2, x3 was 2 and 0, and x4 was 3 and 0, right? So these are your points. Now, so now we need to use the points given the data. We had 4 points, right? If you input the first point, which was 0 and 0, so this one was 0 and 0, right? And the value was here. The value was yn w1 x1 plus w2 x2 plus b, right? So if you put it there, 0 and 0, wn x1 plus w2 x2 plus b, right? The given label for the first point was -1, so it would be -1, right? Because the w was -1. And since these two are 0, x1 and x2 are 0, so this 2 becomes 0. So the only thing remains is the b greater than 1, right? And you multiply -1 to that, and it becomes this. So that's your first point, x1, right? You see, it's pretty easy. For n2, we had 2 and 0, right? And the given class, the y was -1 for that. So that's why you have -1 here, you have 2 and 2 here, and b. N3 was, I'm not sure what that it was, 2 and 0. So N3 was 2 and 0 with the class of +1. That's why you have 2 at the end, this 0, 0 out this one, and you have 2 W1 plus b greater than 1, right? So and then you can do the rest. So now, given these 4 formulas, inequalities, we need to find the value of w and b, right? So do you have any idea how we're going to do that? I mean, this problem can become very sophisticated. That's why we use solvers, a software program that solves Q programming. But in this case, it's pretty easy because so many parameters are 0. So given these 4 inequalities, do you think if I, using number 1 and number 3, right? The first, this one, and the third one. If I add them up, right, these two b will cancel each other, and whatever remains is w1. So using 1 and 3, I can compute w1, right? So here, minus b greater than 1, 2W1 plus B greater than 1, right? So I add them up. It's going to be 2W1 greater than 2. W1 is greater than 1, right? So from 1 and 3, we could find a value for B. Now, find a value for W1. So the same thing, because here we have minus B, it's going to cancel also number 3 as well. So from 2 and 3, so from this and that, you can find the value for W2 as well. So minus 2 W2 greater than 2. So since it's minus, when you divide it, it's going to change the inequality direction as well. So W2 becomes smaller or less than minus 1. Is that clear? Is it clear? All right, so now we use these 4 inequalities to find W1 and W2. Now let's see by having W1 and W2, how we're going to find B now. Okay. So that was your points. So those 4 points. So we use a word sometimes in optimization called relaxation, and it sort of resembles approximation. So you found 2 values, but they're not equal, right? They are inequalities. W1 is greater or equal than 1, and W2 is smaller or equal than minus 1, right? We didn't find the absolute value for that. Thus, the relaxation for that, given this formula, right? If you want to minimize the whole value of this, right? Since they are a square, what would you rather use as W1 and W2? Because they are getting squared, so they are getting bigger, and you want to minimize the final value, right? So given these points that this inequality gives you, so it's 0 and 1, so W1 is here. So if you draw this is your W1, right? greater than or equal than 1, and W2 is minus 1. Right? So these are the values that you can use for W1, and these are the values that you can use for W2. So if you want to minimize the whole value of this formula, what would you rather use from your options? Any guesses? Yeah, that's right. So because you want to minimize the whole value, right? If you, among these options that you have, if you use 1 and negative 1, you're sure that that was the minimum point that could minimize the whole formula, right? You could use 2 and minus 2, but it would become 4 and 4, so the minimization was getting higher. We would like to have the absolute minimum value for the final W1 square plus W2 square divided by 2, right? So the relaxation of this problem becomes W1, 1, and W2 minus 1, right? So now you have the final value for these two. So that's why we call it star, W1 star and W2 star. Now you can put it back in those four inequality you found in the previous slide, and you can easily find B. So this problem yields W star plus 1, W star 2 minus 1, and selecting the same B star as minus 1 satisfied our number 1 and number 4 inequalities in the previous slide. So you found B as well, right? And your formula for your L was W1x1 plus W2x2 plus B, right? Now you have all the values. You have W1 star, W2 star, and also B. Thus, your line would be x1 minus x2 minus 1 equal to 0. And if you draw that, you're going to have this red line here. So this is this. So as you see, it correctly classifies both data, and that's a hyperplane. Okay. Also, as we mentioned last session, the distance between your points and your classifier would be 1 divided by, we would call it P or rho, it would be 1 divided by W, right? So here you see that this line, this point is the closest one. The rho is almost 0.7. This is far greater than this one. So that's why you see this is the one that we need to make sure that the hyperparameter, the hyperplane stays behind, right? So this point decides the distance. And you see, because of this point, now, if you take a look at the figure, because of this point in the vicinity of the SVM hyperplane, these are not relevant anymore. If you even remove these 2 points, the classifier won't change. Okay. So let's talk about how we're going to come up with the definition of support vectors. And that's why we call it support vector machine, because it builds upon the support vectors. So among these 4, there are a vector of data, right? You have x1, x2, x3, and x4. Only some of them, not all of them, are called support vector. So let's see what the definition is. These data points that sit on the boundary, right, play an important role and are called support vectors. So as you saw, this one is a support vector, was the closest one, sits on the boundary. And for instance, this is not a support vector. You can even, if you even remove this point, nothing would have changed, because this, the same line, the same hyperplane would be there, the same margin would be there, right? So this point is not relevant, and that's why it's not a support vector. And support vector decide the value of the margin, right? So for instance, the point 3 and 0, which was this, is also not relevant, because we can even remove it. It's not in the boundary, and removing this doesn't change anything. So this point. So removing it from the data set will not affect the margin. So we could have even removed this one, and the same hyperplane would be found, and the same margin we would have. So these are not relevant, and they are not support vectors, right? This is a support vector. Okay. Okay, let's carry on. So, as another recap, so support vector machine, for a decision boundary, we need to find the line L, W transpose x plus p equal to 0, and for the hyperplane, we need to minimize 1 divided by 2, W transpose t, such that this inequality holds, right? So given every point, we can expand this right? And using these, we can find W star and B star. Using this, we can find the L. So that's the procedure. Okay. As you could intuitively found out, this is a constraint optimization problem, and also there was no analytical solution for that. That's why we need to use a quadratic programming solver or QPU solver. In Python, we have QPU solvers. MATLAB does it, C++, and many other things. So in bigger, even online solvers, there are, just you can Google QP solvers online. There are so many solvers out there. So for bigger problems, you can use those. So the general form of a quadratic programming is when you have an objective function in a quadratic form. So this 2 yields a quadratic function, right? So this is not linear. When your objective function is not linear and is quadratic, and your constraints are linear, by constraint I'm talking about those y and w1 x1 plus y2 wx2 plus b, right, greater than or equal than 1. So this is one constraint. When your constraints are linear and your objective function, which was this, is not, we have a quadratic programming problem. So anytime you have an objective function and you say such that or given that, so this is a constraint that constraint the space for your objective function. So visually you can think about this like, suppose your quadratic form would be like this, right? That was your objective function. Using your constraint your convex shape, like one constraint would be this, one constraint would be this, and one constraint would be this, right? So you use this constraint and you found out, oh, this is the solution space, right? So this is the visual interpretation of that. This gives you a quadratic shape. In higher dimension, you can have more complex shape, and your constraint will constraint that shape in a way that you find a solution space inside. All right. So a general form for a QP problem, quadratic programming problem, is you have to minimize this in general as a generalization. So you have half U transpose QU plus P transpose U, and each of those can define. So this is your constraint. Such that the A matrix, AM of T multiply U, is greater or equal than CM. In our case, this CM was 1, right? So here the optimization is over U, the vector of U, which is a L dimensional space in R. Q is L by L in R. AM is L, and P is L as well, right? So this is a general form for a QP problem. Okay. Also, the bound on U is from Ci and Li. So this is Li. Okay. So in our setup for the SVM, our U matrix would be defined as B as our bias value and W, which is obviously D plus 1. So D for W and plus 1 for B. Our Q matrix is zeros on this end and an identity matrix of D on this side. So you have D plus 1 by D plus 1 dimension. Your P is the D plus 1 dimension as well. So the objective function would be U transpose QU, which is always to the norm square of W. And our constraint would be, as we discussed, Yn multiply B, Yn multiply WT Xn greater or equal than 1. Our Cn was 1, that's why this was 1. And our matrix ANT is Yn, and Xn transpose, which has the D plus 1 dimension. Right, this is just a general form for SVM out of the QP programming. So you can, this is the coefficient of the linear term. Coefficient. Linear term. So P is the coefficient of the linear term. All right, let's have another visual example to see how we're going to find the support vectors here. So we have these three data. Why should we have more? Two sets of data, and out of these x1 up to x7, we see that there are three of them lie on the boundary. So these three are the support vectors, right? And x4 and x5, x7, x6 are outside the boundary, so they're not relevant to our problem. We could have even, removed them. Nothing would change here because this line L only related to these support vectors, right? And that was a distance, that was a margin. Okay, so let's see how we're going to use the support vectors to find a bound for SVM. So suppose x1, x2, and x3 are the support vectors of a decision boundary L as shown, so these 3 points, right? When we use cross-validation, let's see how we're going to find a bound for that. So if you recall from cross-validation, the error involved with cross-validation was the summation of all point-wise error divided by the number, which was n, right? So 1 over n, the summation of n from 1 up to n, en, where the point-wise is computed by leaving out xn and yn from the dataset, right? So you would have to do it iteratively to find the ECV, right? And for the case of the linear perceptron, we saw that by increasing the number of n, which are the points, our dichotomies would increase, so the bound would increase polynomially, right? So let's see SVM, that one of the interesting properties of SVM is its bound does not relate it to the number of n's, but only relates to the support vectors. You see, we have like 7 points here, but 7 doesn't play around with my bound, but only these 3 does, right? And this is a very important property for SVM because when you have a large data set, the training bound would be much smaller because you normally have way smaller support vectors from your data set, right? Another interpretation of this would be if you have this condition, right? And in one of your iterations, say iteration number, I don't know, 6, right? You remove x6 and y6, you removed it from your data set, right? Your error would be 0. It doesn't change because this point was not playing any important role for your classification. Removing this from the data set, the rest would be the same. But changing this tree would change the classifier and would play with the error that you have. So let's see how that plays out. So the first scenario, the first case, for computing the cross-validation error, suppose that xn is not a support vector. So one of those points outside the boundary, like this was the boundary, that was your points. So suppose this point is here, right? It's not a support vector. So when you remove that point from your data set, you have a d minus n, which contains all the points excluding that specific point. And our algorithm on dn will produce the same solution on d as before because this point wasn't playing any important role on the classification. Thus, your error would be 0 here, right? On the case that x was not a support vector. That was a case 1. Is that clear? Why this is 0? So let's see the other case where the point is a support vector. So one of these three. How are we going to compute that ECV? So now, case number 2, the xn is a support vector. So one of the points on the line, so say that was your, say this is one of these points, right? This is your plane. Say this is this point, a support vector, right? Not one of these outside. So by removing this, your estimated y is not going to be equal to the value because you have a misprediction, right? And this value is smaller than 1. So you're going to have error on the case that these two are not equal, right? And the final bound for this ECV is going to be smaller or equal than 1 over n, the summation of all ENs. So you see that in this case, it's smaller than equal. It's not always equal, because some of the points that are not support vector will not have any error. That's why instead of equality, it becomes inequality, right? SV is for support vector. So those points that are support vector will bring this inequality to inequality. And this is always smaller than equal of the number of support vectors. So now we see that the bound for SVM is not related to the number of n itself, just like before, but only relates to the number of support vectors. And this is a very good property because it's going to reduce the dichotomies by a large amount. That's why we mentioned here, note that the ECV is dependent of dimension and only depends on number of SVs. Let me just remove this. You can see it. So the cross-validation error is independent of dimension and only depends on the number of support vectors. And this is one of the advantages of using SVM. All right, guys, I'm going to stop here and we carry on Monday. Any questions? Yeah.
So can you identify the whatever n summation of all the ends is less than equal to 1 over n?
Yep.
Summation of the n if it's a support vector.
Yeah. So when your en, when your n, on the case that your n was not a support vector, right? Your en would be 0. Because if you have some n's here, plus, so that was your margin. Suppose I'm talking about this minus, right? On one of the iterations of the cross-validation, you remove this from your data set and you train on the rest and you evaluate it on this, right? This doesn't play any decision on the hyperplane that you found. So all the time when the point is not a support vector, your error is 0. Right? Thus, when some of the points, the error of the sum of the points are 0, when you add them up, you have like 0, an error, 0, an error. And when you divide it to n, this is always smaller than equal to this one. Right? The final error would be smaller.
So in both cases, the n is the number of data points, but
Yeah. N is the number of data points. And so in one case, x1 and y1 plus, no, not plus. And then xn and yn is the one that you remove, and this is x big N and y big N, right? So you remove this, you train on the rest, and you evaluate on that. The next time, this would be like here. You remove that, and we say that for those cases that this N that you remove on your class validation set, which is the minus, these points have 0 error here. The error would be 0 since L correctly classifies xn, yn. It was, you see, all the time when you have this classifier, and that was not a support vector like it was here, you can even remove it from the data set. Nothing will change here. The same classifier would be found, right? Because it only depends on this tree in this case as a support vector. That's why.
But if you sum over all the data points, the ENs, wouldn't it be strictly equal to summing over all the ENs that are support vectors, because the support vectors belong in the...
Yeah, it cannot be strictly equal. It's a bound. That's why we use the inequality. It's always, smaller or equal. Yeah, good question. Any more question? Right, guys. So see you on Monday morning.